Okay, so I was at the point where I had introduced the discrete and continuous random variables, and an example of a continuous random variable that I had chosen is the normal random variable. And what I showed you with respect to the discrete and continuous cases is that there is a DPQR family of functions that allows you to ask and answer a lot of important questions about the particular distribution that you're thinking about, right? So, for example, with the normal distribution, one important function in R is the R norm function, which allows you to generate simulated data. So in this course, we'll be simulating a lot of data to understand the properties of random processes, right? So that's how we will be using the R norm function. So for example, here I'm generating 5 data points from a standard normal distribution. A standard normal distribution, as you recall, is a normal distribution with mean 0 and standard deviation 1. It's a very important distribution that will turn up quite often. And um, because the mean and standard deviation are specified by default in the R norm function to be 0 and 1 respectively, if you just write R norm 5, you're going to by default be sampling from the standard normal distribution, right? So I can this command, and this command are basically the same thing. But of course, you'll notice that the numbers are different each time because we are generating random numbers, yeah, random data from the standard normal distribution. Okay, the second thing you can do with the DPQR family of functions is that you can ask questions about the probability of observing a particular value or something less than that or something more than that. Remember that in a continuous distribution, asking what the probability of observing a specific number like 2 is is going to always be 0 because probability in a continuous distribution is defined with respect in terms of the area under the curve. Yeah. So, so if you ask a question like, what's the probability of X, that means the observed values being less than 2, equal to or less than 2, uh, in a standard normal distribution is, then you could just type P norm 2, and that tells you the area under the curve to the left of 2. So graphically, what's going on? We should always have a graphical intuition about what's happening here. So if we look here, right, so this is a standard normal distribution, mean 0, standard deviation 1. If I ask a question like, what is the probability of observing a number like 2 or something less than that, right? Notice that these two statements are identical, x less than 2 or s less than or equal to 2. These two statements are exactly identical because the probability of observing exactly 2 is 0, right? So if I ask a question like this, what's the probability of 2 or something less than 2? What I want to compute is the area under the curve from here all the way to negative infinity, right? And that is computed by the P norm function. If I type 2, it gives me that area under the curve, okay? So that's a very important function that we will need in hypothesis testing and stuff like that. Now, if you want to know the opposite, what's the probability of observing a number like 2 or something larger than 2, then there's two ways. One way is to calculate the probability of 2 or something less than 2 and subtract that probability from 1 because that gives you the rest of the probability, right? So graphically, what's going on is if I want to know, right, if I want to know this probability on the right going to plus infinity, then I just want to subtract from 1 the blue probability that I have, the probability that I computed here, right? I just want to subtract 1 from it, and that gives me the red probability here. And the reason for that is that the total area under the curve has to sum to 1 in a proper probability density function, right? That has to be true because the x-axis values, they represent all the possible values that you can observe, the support of x, right? And the probability of observing any of the possible values has to sum up to 1, right? So that's why we can use this method. And the other method that you can use for calculating the probability of X or something larger than, of probability of 2 or something larger than 2, is to set lower dot tail to false. If you do that, it's going to compute the area under the curve to the right of 2. Okay, so these are the two ways to do this. And these two numbers should sum up to 1. Okay, 0.97 and 0.0227, right? So, of course, there might be slight deviations if you sum these up because of rounding errors. Okay, but they should technically sum up to 1. Okay? All right. The third thing that you can ask with the DPQR family of functions, which is very important, is that you can answer questions like using the inverse of the CDF. You can answer questions like, what is the quantile such that um, what is the quantile such that, let's say, 97% of the area under the curve is to the left of it, right? So graphically, it looks like this. So I may want to know, what is this quantile Q, okay, such that the probability of observing this quantile or something less than that is some specific number, let's say 0.975 or something, right? So this area under the curve is 0.975, and I want to know, so I know the probability, 0.975, but what I want to know is, what is this quantile? What is this quantile that gives me that probability, right? So that question is answered by the Q norm function. Q for quantile, right? Q norm function, right? So if I write something like Q norm 0.975, that will tell me, it'll give me a quantile, which is this one here, right? This number will be given back, right? So here, let's look at the example. So you're getting 2 as the value here. The final function in the DPQR family is the dnorm function. And the dnorm function, what it does is that it's telling you the y value in the probability density function, right? So for example, remember that when I write the normal distribution with some mu and sigma as the parameters, right? What I'm really saying is that the function that takes as input x values given some mu and sigma values, right, is like this. It's 1 over square root of 2 pi sigma squared exponential times minus half, and then x minus mu over sigma squared, right? So this is a function that I'm going to be plotting, right? It's just a function, just the same way that you can have a function like this, x plus 1, right? X plus 1 is also a function, right? So if I plug in an x value, it will give me, let's say I plug in 2, it will give me back 3. In the same way, if I plug in a number here, going from minus infinity to plus infinity, any number, that number is plugged in here, and I will get back a number because I've specified the mu and the sigma. So this entire thing in the box will be a numerical value, and that numerical value will allow me to draw this curve, right? So for the number 2, for example, if I plug it into the function, the normal distribution probability density function, I will get back this data point, this value here, right? If I plug for this number here, let's say 1, if I plug in the value x equal to 1 into the function, I will get back this value. So the f of x, mu, sigma, these values are the values on the y-axis that help us draw this curve. And this curve is drawn with the help of the d norm function. D stands for density. So these numbers here, that the f of x is, this function is giving us, these are called the density. They are not the probability. It's pretty surprising that many people get, confused about this because they think that I've seen people mistakenly say that the density values are actually the probabilities. They're not, right? So the meaning of the density, the way to interpret it is to realize that if some numerical value has high density, so let's say 0 here has very high density, 2 has a lower density value, right? What that means is that if you were to sample data from this distribution, you're more likely to get values near 0 than values near 2. Okay, let's check that. Okay, let's check that with simulation. So I'm going to generate, let me generate like, I don't know, just use R norm. I'm going to generate 10,000 data points, okay, from the standard normal distribution. Now, if I plot the distribution of these data that I've just generated randomly, most of the values will be near 0 and very few values will be near 2. Okay, so we can check that. Well, let's do a summary on this, okay? So if you do a summary, you'll see what the distribution is. The mean is near 0. The first and third quartiles, so that means 25% of the data lies below minus 0.69 and 75%, 25% of the data rise is greater than 0.67. Okay, that's the first and third quartiles. And the minimum and maximum values are around 3. But graphically, I can also look at this and you'll see that most of the data that I'm observing is near 0, right? So this is near 0 and near 2, I'm seeing much fewer data points. So that's basically the meaning of the density value. It's not a probability. So you have to be careful about that, okay? All right, so coming back to my slides, right? So this plot now summarizes all the functions that I have told you about in the last lecture and in the I reviewed just now. So there's the R norm function, the P norm function, the D norm, and the Q norm function. So these are the four functions you need to understand because we're going to need them when we start doing hypothesis testing. Because whenever we do statistics, we are always trying to understand properties of distributions. For example, in your Stroop data, right? In the Stroop data, I'm looking at the differences between incompatible and compatible reaction times for the subjects, the 30 subjects that I have, that is you, and that the differences in reaction times that I have is actually coming from some distribution, right? So we have to make some assumptions about what kind of distribution could have generated those data. So that will be the starting point of statistical inference and statistical data analysis. That's why these functions are so important. Okay. All right. So what I'm showing you here is the PDF of a normal distribution with mean 500 and standard deviation 100. And of course, now you should notice that the center point of this distribution here is 500 and the spread is much larger than a standard normal distribution, right? So the code behind all this is of course available to you, so you can look at that later. But I'm using the dnorm function here to produce this plot. I'm plugging in different x values into the dnorm function and I'm getting back this curve here, which I'm plotting here. Okay? The CDF looks like this. This is a cumulative distribution function. That means the p-norm function. It's telling you the cumulative probability of observing 200 or something less than that, 400 something less than that, and so on. And you'll notice that the curve has this characteristic S shape, which asymptotes at 1. Obviously, because the larger these values get to be, what will happen eventually is that the probability of observing a number like, I don't know, 1000 or something less than that will end up being 1 in this distribution that we are talking about. Okay. The inverse of the CDF just flips this curve, just flips the curve so that the x-axis becomes the y-axis and the y-axis becomes the x-axis. So in the inverse of the CDF, the x-axis contains the probability and the y-axis contains the quantiles. So I can ask a question like, what is the quantile? What is the quantile such that 75% of the area of the curve is to the left of it? So that's this number here, right? That's what these things are doing. So you can see that the CDF and the inverse of the CDF are basically the same thing, just flipped. X and Y axis flipped. Okay, so we are just to summarize, so we looked at probability mass functions and probability density functions. And we looked at examples of, these two types of random variables, discrete and continuous, and I've illustrated the use of the DPQR family of function. The next important topic has to do with maximum likelihood estimation. So the idea is the following. First, I've got to explain the meaning of the term expectation and variance. So let's think about it in the discrete case. So the expectation of a discrete random variable, so just call it y. I mean, you can call a random variable with any variable name, right? X, Y, Z, whatever, doesn't matter. So we have a discrete random variable y with some probability mass function f of y that will be, that's defined for that random variable. So the expectation of that random variable, which is written E square brackets and capital Y refers to the random variable itself. The expectation of Y will be the sum of the all the elements in the support of this random variable multiplied with the probability of each of those elements summed up. Okay, so you're summing up, you're taking each of the elements in the support of that random variable, multiplying each of those numerical values with the respective probability from the probability mass function of that particular value, and then summing up the result of that calculation. Okay, so let's look at an example to compute the expectation. Suppose we're tossing a fair coin once, just once. Okay, this is the Bernoulli random variable, right? So the possible events that we would represent as 0 and 1 are tails and heads. Okay, so as I mentioned earlier, this is just a arbitrary decision we are taking to mathematically model the situation that we are looking at. And let's assume that the probability of a success that is heads is 0.5. So in that case, the expectation of this random variable is going to be the sum of y times f of y, right? Uh, so summed up. So what that means is in the support of this random variable, I have 0 and 1 as the possible values, tails and heads. And I'm going to multiply the probability of obtaining a 0 with the number 0 and the probability of observing a heads with the number 1 and sum those values up. And the result I get is 0.5. So 0.5 is the expectation of this random variable, okay? By definition. This is the definition. Okay? Variance is defined in this equation here. I won't unpack this equation for you because it would take us too far afield into random variable theory. But the variance intuitively is just telling us how much variation we can expect in the um, um, in the observed values when we do our experiment, right? So so just to give you a concrete example, right? So if I were to, in the R binomial case, in the binomial distribution, if I were to, right, do one experiment with a sample size 10 with a probability of success 0.5, right? I could get 3 successes out of 10. If I run it again, I get a 4, then I get a 4, then I get a 7. So there's some variability in the number of successes that I get. So let's say I do 1,000 such experiments, right? So well, I'll see a lot of variation in the number of successes in each of these experiments. So you can see that there's a lot of variability because sometimes I just get one success out of 10, right? You see that example there, right? There may even be a 0 somewhere for all I know, right? So I can now compute the variance of these numbers here, and that number, the variance will tell me how variable the number of successes is in the repeated experiments that I have done here on the computer, right? So that's what the variance is telling me, how variable these are. I will of course make this more concrete later on, right? Okay, so the meaning of expectation, both in the discrete and continuous case, will be that if we were to repeatedly do the experiment with a larger and larger number of trials and calculate the sample mean each time of the observations, then we would approach the expected value zero point 0.5. So the expectation is the value that you will get to, that you will obtain if you keep increasing sample size. So in mathematics, we say that this is an asymptotic result. As sample size increases, what will happen is that we will approach the expectation of the random variable. Yeah. So another way to think about the expectation is that the expectation gives us the weighted mean of all the possible elements in the support of X weighted by their respective probabilities, right? So here you can see that the possible elements in the support of X are 0 and 1, and the probabilities are zero point 0.5 and zero point 0.5. So this is a sum, but it's a weighted sum, weighted by the probabilities of each of those possible elements in the support of X, right? So you can think of the expectation as a weighted sum, weighted mean as well. I said weighted sum, but I meant weighted mean. Right. So actually, maybe I'm misstating this. I've misrepresented this here. I'm sorry. Well, I'll fix this later on. But basically, it's really is a weighted sum. It's not a weighted mean. Okay, so I misspoke here. So we are weighting this sum by these probabilities here. Okay, so that's how you can think about it. But I think that this interpretation of expectation is actually a more intuitive one, and it is more useful in the sense that when I know the expected value of a particular random variable, what that tells me is that if I were hypothetically to keep increasing sample size and keep computing the expected value, I would approach this value, right? This is the value that I would get as I keep increasing sample size. Okay, so some important results that we should be aware of. In the binomial distribution, remember the probability mass function of the binomial is this one here, right? And so the expectation of the binomial is n times theta, where n is the number of trials and theta is the probability of success, right? And we estimate the theta. Remember that the theta is the probability of success. In a real experiment, we don't know that probability. We can only estimate it from the data. And the way we estimate that probability of success, which is the way we estimate the probability of success is by computing the proportion of successes divided by the total number of trials. So this result allows us to get an estimate of theta, which is represented as theta hat. Theta hat always represents an estimate of this unknown parameter that we have here. Okay. So, so whenever you do an experiment with, let's say n trials, let me do that. So here's an example. So suppose I do an experiment, single experiment, sample size is 10. So n is 10 here, right? Of course, when I'm generating random data, I have to specify a probability. But in reality, when we actually do an experiment, we don't know what that probability is. I'm just simulating an experiment here on the computer. Okay. So when I do this experiment, what I get is 5 successes. I know what the total sample size is, 10. So my expected value, sorry, my my estimate of theta can now be computed by calculating k over n, where k is the number of successes. In this case, it's 5 divided by 10. What's happening? 5 divided by 10. That's my estimate of this probability. Of course, if I ran this command again, I might end up with a different number, like 6. In that case, my estimate of theta is 6 over 10, which is obviously not correct because I know that in this case, I know that the true value is 0.5, but this is the estimate I have from the data, right? Because the data will have random variability. If I do this again, I get some other number. I can get a 4. In that case, my estimate of theta would be 4 over 10.4, right? I could keep doing these random samples and I could end up with some crazy number like 1 or something like that. Let's see what happens, right? It did happen to us earlier that we got a 1. If I just keep patiently randomly generating data, I will eventually end up with some extreme values like 3. So then 3 out of 10 is my best estimate, is my estimate of theta, even though that's not true, right? So the data will have random variability and the number of successes will give you a way to estimate the theta parameter, right? The probability. The formula for computing the variance in a binomial distribution is the variance of y, the random variable y, will be n times theta times 1 minus theta. So for example, in this particular case, if I had 3 successes out of 10, so my theta hat is 0.3, 0.3, right? 0.3. And that means that the variance, if I were to compute the variance, it would be n times theta hat, that's my estimate from the data, multiplied with 1 minus theta hat, right? So that would be the variance that I have for an experiment with sample size 10 and um, the randomly generated data point 3 from this particular experiment, right? So you can imagine what would happen if I had a sample size of 1 million, okay? So then the variance would change, right? So you can do that yourself. All right. So um, where was I? Yes. So now we know how to compute the expectation and variance of the binomial random variable in a similar way for the normal distribution. That means the continuous distribution. The definition for computing the expectation and the variance is given here. And so the expectation of a normal random variable will be also the sum of each of the possible values in the support of x, or support of y in this case, sorry, multiplied by the density, not the probability, the density of that particular value, right? So this, what I'm doing here is again doing a weighted sum and computing the expectation by summing up these products here, okay? So the whenever you have some data from a normal distribution, what we're going to be doing is we're going to be estimating the mu parameter by computing the sample mean. So this you must have, of course, done in school. The sample mean is usually written by putting a bar over the actual name of the random variable. So the lowercase y represents some actual data that you've collected, and the bar above the lowercase y is representing the sample mean. Okay? So this sample mean gives us an estimate of the mu parameter, and it's computed by summing up all the observed values and dividing by the length of the value. So to give you an example, suppose, so here's my normal distribution. Let's say I generate some 10 data points, right? These are 10 data points that are generated. I'll save them as the vector y. Okay, so these are 10 random data points. If I want to compute the mean of these random data points, I can of course use the mean function, right, which is built in, or I could sum up the values y and divide by what's the length of these values, 10, right? So I get exactly the same numbers here. So the mean function is actually implementing this calculation which I'm showing you here, right? So that's how you would compute the sample mean. So this would be called the sample mean. Similarly, the variance, which tells you how variable the numbers are going to be, is going to be determined by this equation here. Each of the data points y, you subtract from each of them the sample mean, which I just computed here, square that value, okay, and then divide by n minus 1. So, and sum up the squares. So let's start again. You take each of the y values, subtract from each of the y values the sample mean, and square that difference, and then sum up the entire set of values that you get. So let's do that, okay? I'm going to compute the variance. I'm going to compute the variance of these 10 data points, okay? I could, of course, use the built-in function var. That gives me the variance. All right. But let me do it by hand. Okay, so I'm going to compute the variance by hand. So each of the y values, I'm going to subtract from it the mean of those y values, square those guys up, right? If I square them like this, what I will get is a sequence of values now. So I'm going to sum up those values, sum up those values, and divide by n minus 1. What is n minus 1? N is 10, so n minus 1 is 9. So what I should get is exactly the same number that the variance of y is giving me. So this formula is the formula that's been implemented in R when using the var function for variance. Okay? And variance is telling you how variable the numbers will be when you are repeatedly sampling, right? For example, if I were to sample from not a standard normal distribution, but a normal distribution with mean 0, but standard deviation 100 instead of 1, okay? So now if I look at the variance of y, right, it's much larger. And the reason it's larger is that the underlying distribution's standard deviation is much larger. Standard deviation is just the square root of the variance, okay? So that means the variance of the underlying random variable is 100 squared, okay, which is a very large number. All right, so coming back here. So now what we know is, what I'm showing you here is the formulas for the expectation and variance for discrete and continuous random variables, right? What we will mostly need in this course is the is we will need to know how to compute the the estimate of theta in the discrete case, and we will need to know how to compute the sample mean in the continuous case, sample mean and sample variance. These are two important statistics. These are called statistics. These statistics are going to be very important when we are doing statistical inference in the coming weeks. Now, of course, in this slide, I'm just showing you some analytical results, some results from mathematics that we know from previous work. Now, some of you might be curious as to how these results were derived. So these are all provable results. You can prove this mathematically, that the expectation is this, and that the estimate of theta, the best estimate of theta is this quantity here, and so on. All these results can be proven mathematically, and you can find in my lecture notes here, which are online. If you're interested, if you have the mathematical background, you need some calculus for this, you will see the analytical proofs in these lecture notes here, right? So let me just pop up this, right? So if you go to my GitHub repository here, you will find, right, you will find these linear modeling lecture notes. So if you download those lecture notes, what you will find is that, right, if you download these lecture notes, here what I do is I provide all the theoretical analytical results so that you can actually see where they come from. They are not just somebody didn't just make these up, right? They were derived analytically. Yeah. All right. So if you have an interest in the details, you can look at that later on. But in this course, you don't need to know the analytical derivations for these results. You just need to know what the results are, okay, and what they mean, right? You know what the expectation means. You know what it means to have an estimate of mu, right? So we're getting the estimate of the mu parameter in the normal distribution from a random sample of data, right? And that random sample will vary from one experiment to the other, right? So you could end up with different estimates of the sample mean. All right, so this brings us to a very important concept, and the concept is maximum likelihood estimation. So let's take the binomial example, right? So as I said earlier, whenever we do an experiment, so let me just do an experiment and show you. So let me just do this, right? So I just use R binom to do one simulated experiment. I'm going to do n equal to 1, size equal to 10. and probability, let's say 0.5, right? So I get a particular number of successes. That's the number of successes I got in 10 trials, okay? 3 successes. So once I have that those number of successes, I can compute an estimate of the theta parameter from the observed data. So in this particular case, my estimate of theta would be 3 over 10. Okay. So this quantity, quantity theta hat that we are computing, 3 over 10 in my particular example, is the observed proportion of successes. And this number is called the maximum likelihood estimate of the true unknown parameter theta, right? So what's going on here is that when I'm collecting in real life, when I'm collecting data, I don't know what this probability is. I'm just trying to estimate it from the data. The first step in statistical inference is going to be to estimate the parameters of the distribution that is assumed to have generated the data. Okay. So the estimate that I get by using this formula in the binomial case is something called the maximum likelihood estimate of the true unknown parameter theta. So, so what we will do is, the procedure that we'll follow is that we will get the maximum likelihood estimate of theta, k over n, right? And of course, I'll just explain what this means, what the MLE means, right? Maximum likelihood estimate means. And once we have that estimate, we can now compute the expectation. We can compute the variance using the formulas that I showed you earlier, right? These formulas that I showed you. The first step, therefore, is to get an estimate of theta, and then we proceed from there to get estimates of the expectation and of the variance. All right. And then once we have those estimates of the expectation variance, we can do some statistical inference, as I will show you later on. But these are the first steps that we'll be taking, regardless of whether it's a discrete or continuous distribution. Right now, I'm just showing you the discrete distribution. So now the interesting question is, I keep using the phrase maximum likelihood estimate, but what does it mean? Okay, so I'm going to explain that now. So to understand what a maximum likelihood estimate is, you have to understand what the term likelihood means. So if you remember in the binomial case, right, in the binomial distribution, I defined a probability mass function f of, I don't know, what was it, k, given n trials and theta as the probability of success. So the probability mass function was n choose k, theta to the power of k, and 1 minus theta to the power of n minus k. Okay. So this probability mass function is actually dependent on two values, the sample size n and the probability of success theta. The only variable in this probability mass function, the only variable is k. This is the variable. Everything else is fixed. N and theta are fixed. So this function is a function of k, right? But we can actually interpret this function as a function of theta instead of being a function of k. So what that means is once I do an experiment, so let's say we do an experiment. When I do the experiment, I know what n is. So let's say n is 10. And once I've done the experiment, I know what k is also, right? So k could be 3, as in my example, which I just ran earlier, right? So these two numbers are now fixed, right? So we could take the same function, f, and treat that function as a function of theta, because k and n are now known, right? They're already fixed values. So we got 10 choose 3 times theta to the power of 3 and 1 minus theta to the power of 7. Right? So this function now is a function of theta. So when we see the probability mass, we can look at the probability mass function in two ways. One, we can use it in the way that it is actually defined. as a function of different values that you can get in the support of the random variable, or you can, having done the experiment, you can treat it as treat the same probability mass function as a function of theta, because theta is an unknown value, as I said. We are always going to be trying to estimate theta from the data. So we can think of the probability mass function as being a function of theta instead of k, because k and n are fixed once we've done the experiment. So once we do that, what you will notice is that if you have k equal to 3 and what is it, n equal to 10, right? What will happen is that this function, the function described in terms of theta, so x-axis is theta, what will happen with this function is that this function will have a shape like this. So of course it ranges from 0 to 1, and the maximum point of this function here for this particular data is going to be at point 3. The maximum point is the point where the curve has the highest value, right? So this is the maximum point here, and so it's actually a turning point here. So the curve keeps going up, 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 up. Here it flattens out and then goes down here. So this is the maximum point in this curve, right? And so when we say that we are going to compute an estimate of theta given this data, we're going to compute the estimate of theta by doing this calculation, k over n. This is the k over n calculation, right, that I showed you earlier. What we are computing is the point in this function of theta. We are finding this point here on the x-axis such that we are at the maximum value here. That's why this k over n is called a maximum likelihood estimate, because this equation here, which is a function of theta, is called a likelihood function. Likelihood function. It's the same function as the probability mass function. It's exactly the same thing, but the likelihood function is a function of theta, and the probability mass function is a function of in this particular case, of k, right? So that's the difference between the meanings of the probability mass function and the likelihood function. So what I've drawn here is the likelihood function, right? And this likelihood function is sometimes just written like this, curly L theta, just to represent the fact that the input on the x-axis is going to be the theta values, so values ranging from 0 to 1, and the curve will be of a particular shape, and the maximum point of that curve, that is the maximum likelihood estimate, will be determined by the value k over n, which is this number here. Okay, so that's the meaning of the maximum likelihood estimate. So So let's see if we can actually visualize this, okay, a little bit. So to repeat the concrete example that I said I showed you earlier, so suppose I have n trials and 7 successes, the likelihood function will be written like this. Okay, so we will have the function being it's a probability, it's the probability mass function, but written as a function of theta. So we'll write curly L, um, and then theta is the variable of interest now, and k and n are known, and therefore you can see that the function actually only depends on theta now. So graphically, what that would mean in this particular case was n is 7, when n is 10 and the number of successes is 7, what you will notice is that the maximum point in this likelihood function, the maximum value is at 0.7. If I had gotten 3 successes out of 10, then the maximum value would not be at 0.7, it would be at 0.3, okay? Like I showed you earlier. So that's why the quantity k over n, which is the estimate of theta, is called a maximum likelihood estimate, because it tells you what this value is on the x-axis such that the likelihood function is at its maximum value here. That's why it's called a maximum likelihood estimate. Okay. And this, what we're looking at here, is the likelihood function. This one here. We're looking at this function here. By plugging in different values ranging from 0 to 1 for the theta parameter, we are able to draw this curve here. Okay. All right. So of course, all the code for all this will be available to you on Moodle, so you can try it out yourself, right? With different values of k, like you can put in 3 here. Then what will change is all the sevens will change to 3, and then the shape of this curve will also be different, right? It'll be the maximum value will be over 3, for example, zero point 0.3, sorry. Okay, so as I explained or tried to explain, the maximum likelihood estimate gives us the most likely value that the parameter has given the data that we have observed. So in the binomial, the way we compute this maximum likelihood estimate is by computing the proportion of successes. And this can be proven to be a maximum likelihood estimate. That means whenever you have some data with k successes in n trials, if you compute this proportion k over n, that number is guaranteed to be the point on the x-axis such that the likelihood function is at a maximum point at that particular value. This can be proven, right? It's in my lecture notes, in the linear modeling lecture notes that I mentioned earlier. In case you're interested in the mathematical proof, you will be able to see it here in these lecture notes. But you don't have to read these lecture notes. You're not required to read them. It's only if you're interested. Yeah. All right. So that's the idea of a maximum likelihood estimate. And if you're interested in reading more about maximum likelihood estimation, you want a more formal treatment than the one that I gave. I did a very informal presentation here of the MLE. You can read this nice book, which is available for free online, and it will give you more details on maximum likelihood estimation. But of course, it requires some calculus, so you should be ready for that if you're interested in understanding this more deeply. Yeah. So one important thing to understand about the maximum likelihood estimate is that um, when we take a particular sample with a from of data from with a particular sample size, we will get an estimate the um, uh, of the parameter of interest. So in the binomial distribution, for example, the theta parameter will be estimated by k over n, but that theta parameter's estimate need not reflect the true value of theta. I already showed that to you. Like if we get 3 successes out of 10, right, in this example here, right, we know what the true value of theta is, but our estimate is quite far away from that true value, right? So any one particular sample need not give you the true value of the parameter of interest. It will give you an estimate that may or may not be anywhere near the true value. And so what I'm trying to show you here in this plot is that as you increase sample size, what the maximum likelihood estimate from a particular sample does is that as sample size increases, we get close to the true value of the parameter, right? But for smaller sample sizes, there will be variation in our sample sizes, such that with the consequence that the estimate of the parameter of interest can be wildly off from the true value, right? So what you have to remember is that the maximum likelihood estimate uh, is the best estimate of the parameter, but that's an asymptotic result. That means that the claim is, or the mathematical result is, that the maximum likelihood estimate will give us an accurate estimate of the parameter value in the limit. What that means is, as we increase the sample size, we will eventually get to the true value of the parameter. But if you have smaller sample sizes, there will be variation around from one sample to the other. There will be variation in the estimate of the parameter. And we could be wildly, off the estimate. We could be wildly far away from the true value of the parameter. So in this particular figure, the true value of the parameter is 0.7. So that's this horizontal line. And you can see that in the smaller sample sizes, there's a lot of variation in our samples estimates of that parameter, but that variation starts decreasing as we increase the sample size, and eventually we start getting estimates of the parameter that are exactly the correct estimate. Okay, so that's what I want to explain, that a, from a particular sample, when you take a particular, do one single experiment, you get a particular estimate of the number, you get a number of successes in the binomial case, you compute an estimate of the theta parameter. That estimate need not reflect the true value. Yeah? It would reflect the true value if you had a sufficiently large sample size. Yeah. So, so we've talked about expectation and variance in discrete and continuous cases, and I've shown you how we can estimate parameters in the binomial by computing k over n, the proportion of successes. We can also estimate the mu and sigma using the formula shown earlier, right? So these will be important first steps, estimating, getting estimates of the parameters in whichever distribution we are talking about, discrete or continuous. The first step will always be to get an estimate of the parameters of interest. And which parameters are of interest will depend on which distribution we are talking about. Okay? So that's all you need to know right now about maximum likelihood estimation, right? But I'm going to, of course, return to this topic later on when it becomes relevant. So the next thing we'll discuss in this lecture is bivariate and multivariate distributions. And so let me now explain what that is. So let's start with a discrete case. So this is actual data from one of my former students' PhD thesis. And so what my student Anna Lorena Vichuta did is that she collected data from subjects where in every trial, she didn't just collect a yes/no response, but she collected a Likert rating as well. So she got subjects to read a sentence. They had to give an answer which could be correct or incorrect, right? So that's this random variable here, which is a binomial, right? And but she also in the same trial asks subjects to rate the sentence on a scale from 1 to 7. So 7 is acceptable and 1 is unacceptable, right? So this is called a Likert scale, right? So what we're getting from each subject in every trial is 2 data points. So we're getting data from 2 distributions. One is a binomial distribution, and this distribution here with the Likert scale responses is called a multinomial distribution, right? So, so what we are really looking at is a situation where we have 2 random variables which are somehow jointly operating to give us a 3-dimensional distribution. That 3-dimensional distribution here is called a bivariate distribution because there are 2 variables involved here. Okay. Earlier we had looked only at univariate distributions like the binomial and the normal, right? Those were univariate. So now we are looking at a situation where there are 2 variables involved and they are somehow related to each other. And we can graphically summarize the relationship by looking at this 3-dimensional plot here, right? So on this axis here, the y-axis is the binomial random variable. On the x-axis here, I have got the multinomial random variable. And on the y-axis, I'm getting the probabilities of getting different x and y values. So x equal to 1 and y equal to 1 and x equal to 1 is the height of this box here. And similarly, for all the other things, I'm getting a joint distribution of the x and y values, right? And so mathematically, the way we would write the joint probability mass function of the 2 random variables x and y. So now we're talking about a probability mass function for 2 random variables considered simultaneously, right? So we are talking about the joint probability mass function where the x values range from 1 to 7 and the y values range from 0 to 1. So this, what you're seeing here is just this 3-dimensional figure numerically stated. Okay, so they're exactly the same thing. So we are looking now at the joint probability mass function in a bivariate distribution, and that's written like this, instead of writing P of X or P of Y, which would be um, univariate distribution for x and y. We're talking about the joint distribution of x and y. And so that's what we mean by bivariate case here. Okay. So we can actually, once we know the joint probability mass function, that's this function here, right? We can actually derive the marginal distribution of the x and y random variables. So basically what we are doing here is, what we are trying to do is, for the random variable x and the random variable y, we are trying to derive the probability mass function for each of those random variables from the joint probability mass function. So we're going to start with the joint probability mass function, and we're going to work out the probability mass function for y and for x independently, so separately. So the probability mass function for x is going to be looking up the joint probability mass function of x and y and summing over all the y values. So when I want the probability mass function of x, what I will do is I will go to this figure, this table here. I will, for x equal to 1, I will sum up these two values. For x equal to 2, I'll sum up these two values. X equal to 3, these values, and so on. And the result of summing those up, I'm going to write in the lower border here. In this margin here, I'm going to write the the what would eventually then be the marginal distribution of the random variable x. So let's look at this. Okay, I'm going to compute this. I'm also going to compute the marginal distribution of y. And the way that would work is I would look up the joint probability mass function. That's this table here. And if I want to figure out the um, probability mass function for y, I'm going to sum up all the values for x equal to, for y equal to 0 and for y equal to 1, and write the sum in the margins here. And that would give me that marginal sums. Those marginal sums would give me the distribution of y equal to 0 and y equal to 1. So that means the probability mass function for that particular binomial random variable. So let's do this, okay? So I'm going to do this calculation. And once I do this, you see that I've added the margins here, the probability mass function for the binomial random variable y, which has values 0 and 1 in the support of x of y, and then the marginal distribution of the random variable x, right? Where x, the support of x is these 7 numbers, that is, these are the possible numbers. So here's the probabilities of each of those 7 numbers here, right? So just focusing your mind on the probability mass function for the random variable y, what this is saying is that the probability of success is 0.709 and the probability of failure is 1 minus 0.709, which is 0.291, right? So these two should sum up to 1. These probabilities should sum up to 1 because these are the only two possible things that can happen in a binomial. And in the Likert distribution here, the multinomial distribution, for each of the x values, I've got a probability of that x value appearing. And these numbers will also sum up to 1, right? So it's possible that if you sum these numbers up, they don't sum up exactly to 1. That's because of rounding errors, because I rounded these to three significant digits. So there could be slight deviances from 1, but in principle, they will actually sum up to 1, right? If I were to not round the numbers. Okay. And so graphically, it's important to understand what we are doing here. Okay. So if you look at the joint distribution, the joint distribution is this original plot, this figure that I showed you. This figure that I showed you, or this plot here, this is the joint probability mass function of the random variable, the joint, the two random variables x and y. What I'm showing you now is the probability mass functions of the two individual random variables of p of y. That's the probability mass function for the binomial. And for the multinomial, we are looking at another probability mass function here, right? So this is all familiar to us, right? The univariate case is familiar to us because we already looked at the binomial case before, right? So what I'm showing you now is that given a joint probability mass function of two random variables, we can derive the univariate probability mass functions for each of the two random variables. So we can get that from the joint probability mass function. All right. So another important thing that one needs to understand is how to compute the conditional distribution of x given y. So, and the conditional distribution of y given x. What that actually means is the following. So let's go back to this joint probability mass function. I can now ask questions like, when x is fixed at 1, what's the distribution of y? If x is fixed at 1, what's the distribution of y? You can see that it's different when x is fixed at 1 and x is fixed at 2. These numbers are different, right? So the distribution of y is going to be different depending on what the fixed value of x is. And so the fixed value of x is represented like this. You're going to say here, for example, in the second equation 16, what we are asking here is what is the distribution of y when x is fixed at a particular value? So the y given x is called the conditional distribution of y given x. So this is how it's written. And by definition, right, the way we define conditional distributions is that we can compute for every possible fixed value of x, we can compute the distribution of y, right, by looking up the joint distribution of x and y. That's this table here. This is the joint distribution, right? And dividing the joint distribution by the marginal distribution of the marginal probability, right, of that particular x value. So that sounds very abstract. Okay. So let me make this more concrete. What we're trying to find out with these equations, what's useful to know with these equations is that what we want to know is, for example, okay, I might want to know the distribution of y given the um, given the case that x is fixed at 1. So I'm trying to find out the conditional distribution of y given that x is equal to 1. So the way I would do that is that I would look up the joint distribution of x and y, which was the table, and notice that x will be set at 1 right now, will be fixed at 1. We fixed it. Divided by whatever the probability is of x when it has the value 1. This we had computed earlier. If you remember, when I computed the marginal distribution, where's my table? Let's go back. Yeah, here. X equal to 1, I know what the marginal distribution of x is when x is equal to 1. So that will be in the denominator. That will be in the denominator. Oops. What did I just do? Sorry. That will be in this denominator here. It will be 0.049, was it? What was the number? Yeah, 0.049, right? That would be in the denominator here. And I just need to figure out what to put in the numerator. And when I figure that out, I will know the conditional probability of y, okay, given x equal to 1. Now, what are the possible values that y can have? Y can have the possible value 0 or 1, right? If you remember in this table, y can only have the value 0 and 1. So what I want to know is, what I'm going to compute is the probability of y when it's equal to 0, given that x is equal to 1. How would I do that calculation? Oh, sorry, can't see this. How would I do this calculation? Well, what I have to now do is I have to compute what the joint distribution of y equal to, y equal to 0 is, and in the case where x is equal to 1. This I can figure out by looking up the table, right? Because what is the probability of y equal to 0, x equal to 1? Let's go back to the table. That's this number here, 0.018, okay? Divided by, so this will be 0.018, right? This quantity divided by the probability of x equal to 1, which I just established is 0.049, right? So this quantity, the probability of y equal to 0 when x is equal to 1 is going to be 0.018 divided by 0.049, right? Similarly, I can now ask a question like, what's the probability of y being equal to 1 given that x is equal to 1? So again, I'm going to compute y equal to, what is it, 1, x equal to 1 divided by probability of x equal to 1, which I can look up. I can look up this numerator, right, in the joint probability mass function. For y equal to 1, x equal to 1 is 0.031, 0.031 divided by, again, 0.049. And so then I get the probabilities of y equal to 0 and y equal to 1 given that x is equal to 1. So that's how the conditional probability is calculated. Okay. So that's what I'm doing here, right? So where's my, yeah. So Um, so what I did here is I'm doing the other calculation here of x given y. So I did the simpler one for you in the in this example that I just worked out. I computed this conditional probability distribution, but I could have computed the equation in 15, right? So the conditional probability of x given some particular value of y, right? So that's what I'm computing here. So you can work this out yourself and you will see how the conditional probabilities are calculated. So I could actually write down a table now, which gives me the conditional probability, conditional distribution, sorry, of x given different values of y. Either y would be 0 or 1, and I could fill in this table now, right, by using the conditional probability rule. So I would strongly advise you to take a few minutes to sit down with this equation, the conditional distribution of x given y, and using my example here I'm using the example of x equal to 1. So x equal to 1 and y equal to 0, right? I'm starting here, right? And using the conditional probability rule, the conditional distribution rule, sorry, what did I call it? Yeah. So for computing conditional distributions, the definition that I gave you, just plug in the values, right? You take the joint value of x equal to 1 and y equal to 0. X equal to 1, y equal to 0 is 0.018. That's this number here, divided by the marginal probability of y being equal to 0, right? So I can look that up. Where is y equal to 0? Here. Y is equal to 0. Here, the marginal distribution, I computed it earlier, 0.291. So that goes there. So this is the conditional probability of observing x equal to 1 when y is equal to 0. Okay, so this is a very important idea that will become very useful for us when we do more advanced, statistical analysis in the second part of this course. And if you stick around in my statistics classes and do the Bayesian course later on, right? These are very important concepts that will turn up over and over again, right? So right now, luckily for you, right? You don't actually need to be able to do these calculations for the rest of this course, but I do want you to be aware of the fact that you can actually compute conditional distributions from joint probability mass functions. So given a joint probability mass function of two random variables, right? You can always figure out the probability mass functions of the individual random variables. That means the marginal distributions of those two random variables. And having done that, you can figure out the conditional distributions of each of the random variables given specific values of the other random variable. So whenever you have a joint probability mass function, you can work out two other distributions from them. One is the marginal distributions of the two random variables, and the other thing you can figure out is the conditional distributions of x given y or of y given x. And these are the pieces of information you get out of the joint probability mass function. Okay. And this is, of course, the discrete case that I'm showing you, but the same situation holds for the continuous case. If you have a bivariate continuous case, which I will just show you in a moment, then you can work out the marginal distributions and of the two random variables, and you can work out the conditional distributions. And I will give you an intuition, graphical intuition for that in a moment, okay, for the continuous case. So that's the discrete case. It's a good example that gives you a good intuition for how, how you can use um, a joint probability mass function in the discrete case. What is it good for? It's good for deriving the marginal distributions and the conditional distributions. And of course, for describing the joint distributions of the two random variables. So now let's turn to continuous bivariate random variables, and multivariate distributions are just a generalization of the bivariate case. So I will only discuss the bivariate case for now. And then later on, when we do more advanced data analysis, you will encounter many cases where there will be multivariate distributions. So the situation I want you to imagine is that, let's say we have two normally distributed random variables, x and y, and assume for now, just for simplicity, that the two random variables have a standard normal distribution as the underlying PDF. Yes, standard normal distribution in the two random variables. Mathematically, I would write it like this. Okay? So I would say that x, the random variable x, is coming from the standard normal, and I would say that the random variable y is also coming from the standard normal. Okay. But I want to specify one more detail, one that connects these two random variables. What I want to say is that there is some correlation. I want to assert, I assert now that there is some correlation between the two random variables, which I'm going to write like this. So this is the Greek letter rho. It's pronounced rho, R-H-O. And so what I'm writing here is that the correlation between x and y is some numerical value rho, right? So the correlation, as you probably know, can be a number that ranges from -1 to +1. A correlation of 1, would represent something like this graphically, right? A positive correlation of 1, if the rho value of x and y was 1, it would look like this. If the correlation were negative, right, -1, it would look like this, right? Rho xy is -1. If the correlation was 0, it would look like this, right? Rho xy is equal to 0. So So we are describing a relationship between the x and y values through this rho parameter, and this correlation parameter, right? So this kind of distribution where there are two random variables, where the two variables may be correlated with each other, how do we write that down mathematically, right? One way to do it is, of course, the way I just did it, right? So I could say that I have two random variables, standard normal, and the correlation between x and y is whatever the number is that I think it should be, let's say 0.5 or something, right? So I could actually describe the relationship between x and y like this. But there's actually a different way in which we will write this. And the way we will describe a bivariate distribution like this is that we will say that the two random variables are coming from a bivariate normal distribution. That's what the subscript under the n is. And each of the two random variables, x and y, has mean 0. So I'm going to write this in matrix notation, right? So this is a 2 by 1 matrix, right? Basically. And this matrix is describing the means of each of the two random variables. So the mean of x is 0, mean of y is 0, because they're standard normals, right? And so what's interesting here is that I'm going to describe the standard deviations. See, normally in the normal distribution, we would write a standard deviation here. But now that we are talking about a bivariate distribution, we can't just write a single standard deviation here because there's two standard deviations involved, right? So we need to have a way to express the standard deviation of x and the standard deviation of y. And the way we do that is by, sorry, we do that by writing something called a variance covariance matrix, which expresses both the standard deviations of the two random variables and the correlation between them. And the way we do that is that we will write a matrix. This will be a 2 by 2 matrix now in this bivariate case, where in the diagonal part of this matrix, so this part of the matrix which I've just circled is called the diagonal part of the matrix. We will write the variances of the two random variables. So here in the top left, I will write the variance of the x random variable, and on the bottom right, I will write the variance of the y random variable. So on the diagonals, we will write the variances of the respective random variable, and in the off diagonals, this is the off diagonal here, right? I'm going to write something called the covariance of the two random variables. The covariance of two random variables is defined as the correlation rho times the two standard deviations. Correlation times the two standard deviations. Right? So the covariance written like this of two random variables is defined to be the correlation times the two standard deviations. Right? So this matrix, this 2 by 2 matrix, is called a variance covariance matrix. So I'm writing it in abbreviated form as a VCOV matrix, variance covariance matrix. And the reason it's called a variance covariance matrix is because in the diagonals I've got the variances, and in the off diagonals I've got the covariances. So the way we will describe a bivariate distribution like this is in terms of the variance covariance matrix and the means, the two means of the random variables. Okay, so that's a complete description of the bivariate, the two distributions that are correlated to each other. So this is how I would write the variance covariance matrix. It's traditional to write it as a big sigma here, right? So this becomes easier to write because now what we can do, right? Let me go back to my iPad. So if I want to write the bivariate distribution for the random variables x and y, I would write whatever the mu's would be. And here I would just write big sigma instead of writing the variance covariance matrix, because the big sigma actually represents the 2 by 2 matrix in this bivariate case, right? The one that I just wrote earlier, right? So it's just conventional to use the big sigma notation to represent uppercase sigma to represent the variance covariance matrix. Of course, you should not be confused now. Try not to be confused by the fact that this big sigma is also used to represent summation, right? So when we are calculating the mean, when we're calculating the sample mean, I've shown you before that I would use the sum of x sub I, all the values, divided by the sample size, right? Here also we are using big sigma, but that big sigma is now representing a summation of those x values. So the meaning of the big sigma depends on the context in which it's being used here. So here it's not a summation, but rather it's representing, sorry, where is it gone? Where is it gone? I thought I just wrote here, right? So here it's not representing a summation, but rather the variance covariance matrix. Yeah. From context, it should be clear what the meaning is here. Yeah? Okay, so basically, what this mathematical statement is describing is the joint probability density function of the two random variables. Okay, so now I'm going to visualize that for you. So remember that I said that x and y are standard normal distributions, right? So we can now visualize the standard normal distribution. Let's skip all this and let's skip all this. Let's get to the visualization for now. Okay. So what I'm showing you here is the X and Y distributions, right? You see this? These are the X and Y distributions here. And we are looking at a distribution, the joint distribution of X and Y, where X and Y are both standard normals, where the correlation between them is zero. There's no correlation at all. And so what we are looking at is the distribution of X and the distribution of Y jointly. And because this is a three-dimensional plot now, This distribution has the shape of a smooth cone with a smooth shape on all, uniform shape on all sides. No matter how you look at this cone, it'll look the same from all sides. And if I look at this cone from above, if I take an aerial view of that cone, for a correlation of 0, I will see a smooth round cone, right, in this three-dimensional situation. What we are looking at in the bottom plot is the cumulative distribution function of x and y, right? So I can use this distribution function to figure out the probability of observing a value like this one or something less than that, and the probability of a value of y being this number here or something less than that by looking at the surface, the not the area but the volume under the curve, that I'm seeing is this, in this three-dimensional plot. So basically, once I know the probability, the joint probability density function of x and y, I can describe it graphically if I know the correlation between them, right? And I can also derive from the probability density function, joint probability density function, I can derive the cumulative distribution function, right? Which allows me to compute the probabilities of observing a particular set of values for x and y or something less than that or something more than that. Just like in the univariate case, no difference except that we're talking about two variables here, okay? So what happens when the correlation is not zero? What is the shape of this joint probability density function? Let's take a look at that, right? If the correlation were negative, let's say, what would happen is that the cone, the smooth cone that you're looking at here, would get crushed in a particular direction, right? It would be, if I'm looking at it from above, the three-dimensional plot here, you'll see that as x is increasing, y is decreasing. So you see this curve, this crushing together of the cone in this direction when the correlation is negative. Yeah. Similarly, when the correlation is positive, what would happen is that the cone's shape would change and it would be, crushed in this direction. When x is increasing, y is also increasing. So the shape of this cone is actually going to change depending on the correlation that we have, right? Now, the interesting thing for us now, this is the visualization, of a bivariate distribution. And, in these slides, I only talk about bivariate distributions, but you could imagine having more than two variables. You could have X, Y, and Z. You could have three random variables that could represent a multivariate distribution. So I would write it like this, X, Y, and Z. So these are three random variables now, and they're coming from a multivariate distribution with three dimensions. So if these are standard normal distributions, then each of these would have mean 0. And then I would have to write a gigantic variance covariance matrix that would have dimensions 3 by 3, because along the diagonals, I would have the variances, oh, sorry, Z, right, of the three random variables. And in the off diagonals, here, here, I would have the covariances. So here I would have the covariance of x and y with the standard deviations of x and y. Then, sorry, the correlation of x and y multiplied with the standard deviations of x and y. Similarly, here I would have x and z correlation and the standard deviations of x and z. Can you see this? And here I would have the correlation of y and z multiplied with the standard deviations of y and z, right? So on the off diagonals, I would have the covariances and I would have exactly the same things here, right? This quantity would turn up here, this quantity would turn up here, this quantity would turn up here, right? So the variance covariance matrix would get bigger and bigger depending on how many, variables we are talking about. So this is just a multivariate distribution with 3 dimensions. I could have a multivariate distribution with 16 dimensions, right? The reason I'm not showing you these distributions in the slides is because it's very hard to visualize a 16-dimensional situation. This is a 3-dimensional plot. This I can visualize, but trying to visualize a 16-dimensional multivariate distribution is difficult, so that I don't even try, right? So that's why I'm trying to give you the intuition for what a bivariate distribution looks like in the continuous case. And then the generalization of that is the multivariate case. Okay. All right. So where was I now? Right. So now the interesting thing for us is how to how to simulate data from a bivariate distribution. Okay, so what do we need? What are the ingredients that we need to simulate data from a bivariate distribution? Let's go back from first principles and see how we would generate data from a bivariate distribution. Remember that I have defined the means of the two distributions to be zero, and I've defined the standard deviations to be something, like one, let's say, for each of the two random variables. And so therefore, I can actually define the variance covariance matrix provided I specify some correlation. Okay. So my first step for generating, the random data would be to define a variance covariance matrix, define a vector of means, and then use some function in R to generate random data. Remember, for the univariate case, how do I generate random data? If I want to generate random data from a standard normal, how do I do that? I use the R norm function, right? This would generate 10 data points from this distribution. What I want to generate now is data from a bivariate distribution. And for that, I'm going to specify some correlation between the two random variables, right? And we are going to use a function like the R norm function, but a function that will produce multivariate data. So this is multivariate R norm is a function that we are going to use to produce simulated bivariate data. So what I do is, first of all, I'm going to define a variance covariance matrix that is a big sigma. And what I'm doing here is I'm just assuming that the variance covariance matrix has the following properties. So the variance of the first random variable is 5 squared. I could have chosen 1 squared, okay? It doesn't matter. I'm just using an example here. And the variance of the second random variable is 10 squared, okay? And therefore, the covariances are going to be the correlation, which I'm assuming to be 0.6, but multiplied by the respective standard deviations. So if I run this code, let me try to run this code, okay? What this code does for me is that it allows me to define a variance covariance matrix that looks like this. Okay, so I've got on the diagonals, I've got the two variances. In the off diagonals, I've got the covariances, right? So the covariances are defined here and here, and they're landing in this region here. They show up in this region in the variance covariance matrix. So now I've defined sigma, big sigma, right? And so let's go back here. We're going to use the mass package. So there's a package called mass, which you can install with the install packages command as usual. And there's a function called, oh, sorry, I actually wrote mr norm. I meant mvr norm. So this is the multivariate R norm function, which generates 100 sets of data points where the mean is defined for each of the two random variables. Here I'm defining it as 0. And the big sigma is the big sigma that I just created here. Okay, that's the variance covariance matrix, right? So if I were to run this command now, so let's do this, okay? If I were to run this command in R, what this would produce for me is it would produce 100 data points. So there's 100 rows here. And notice that what it's producing is not a univariate set of random data. In the R norm function, we were getting univariate data. It's producing bivariate data. So these sets of values are now correlated to each other. And I can actually view that. So let me just plot the correlation, between the first column, plot U column 1 against, and on the y-axis, I'll put column 2, okay? So let me just plot this correlation. And you see that there's a positive correlation between these two guys here, right? If I had set my big sigma to be negative, right? Let's go back here. Oh, sorry, where is it? Here, right? If I had defined my variance covariance matrix in the following way, right? Let's do this again. If I'd set this variance covariance matrix such that the correlation was not plus zero point 0.6, but minus zero point 0.6. Okay. Now, if I generate random data, now I'm going to generate some random data with a variance covariance matrix which expresses a negative correlation between the two sets of values from the random variables. If I now plot these guys, you see that there's a negative correlation here. And if I had set sigma to 0, let's do that. Okay, let me set sigma to 0. So now I've got two independent random variables with no correlation between them, right? If I were to generate data again with a new variance covariance matrix such that the covariances are 0, that means the correlation is 0 between them. If I were to plot these, you would see that there's no discernible correlation anymore between these two guys, right? So basically what we are doing here is that what we have learned is how to generate random data from a bivariate distribution, having specified the means of the two random variables and the variance covariance matrix for those random variables. Now, this is a completely general method for generating random data. And the reason I'm showing you how to do this, how to generate random data using the MVR norm function, is that later on in the second part of this course, we'll be generating simulated data to understand the properties of our statistical model. And we'll be in a situation where we'll be modeling multivariate distributions of this type, right? Not just bivariate, but multivariate. So there could be three random variables that we are talking about. In that case, we would have to define the means for each of those to generate simulated data, and we would have to define a 3 by 3 variance covariance matrix to produce simulated data. So this is a very powerful tool for understanding the properties of statistical models by simulating data. And that's how we'll be doing this. That's why I'm teaching you how to do this. Okay, so this is just the plot showing you how you can generate positively correlated bivariate distributions and so on, right? Okay, so to summarize, what you should now know and be familiar with is several foundational ideas. You should know what a probability mass function is in a discrete random variable, what a probability density function is in a continuous random variable. You should know how to use the DPQR family of functions. Okay. You should know what a likelihood function is and what a maximum likelihood estimate is. Regarding bivariate distributions, you should know what the joint probability mass function is in the discrete case. You should know how to compute the marginal and conditional distributions given a joint probability mass function. Okay. These are the foundational ideas that you need to be clear about in your mind before we get into statistical hypothesis testing and statistical inference in general, right? So the next topic that I will now work on is doing hypothesis testing. I will work with the Stroop data, okay, to give you an idea of how the hypothesis testing framework is set up, okay? And when we do the hypothesis testing work, we are going to refer back to the DPQR family of functions. We're going to need this knowledge that we have in chapter 1 in order to talk about how the statistical inference actually works. If you don't understand chapter 1, the DPQR family, if you don't understand what a likelihood function is, what a maximum likelihood estimate is, you're going to have difficulty following the rest of the course. Okay, so this is a very important foundational section that you need to pay attention to. Okay, so now one question that came up in the class was that one of you was very enterprising. Okay, maybe others also tried this. You tried to run the code for the bivariate distribution, and you probably did not succeed in doing this because what would have happened is that, right? So for drawing a figure like this, you need some packages for drawing this figure. So let me just show you how to install those packages. So what happens is that in most of the packages in R, most of the packages in R are actually available here on the CR archive network, right? So it's been a long time since I looked here. Packages, right? If you look at packages, you'll find all the available packages sorted, etc., etc. And so one of the packages that I use in the R code is the bivariate package. So the bivariate package is actually no longer here, right? You try to download, if you try to do this, right? Install packages. Let's go to install packages. Oh, where is it? Sorry. Tools here, right? If I try bivariate, I'm going to get an error probably, right? Right. So it says warning, bivariate is not available in this version of R. A version of this package for your version of R might be available elsewhere. See the ideas at CRAN manuals patch, blah, blah, blah. That's not super helpful as an explanation. But what you can do is you can type CRAN bivariate on Google, right? Yeah. So this gets me to this bivariate package here, okay? And it says here, this package was removed from the CRAN repository. The reason for the removal is actually really stupid. So what happens is that in order to put up a package, to be allowed to put a package on the CRAN repository, you need to pass some tests, right? So the administrators, people, the people who run the R programming language, they demand that every package that is put on the archive has to pass some tests, right? And so their tests are very obscure because they have tests for running the packages on the Solaris system, which nobody uses anymore anyway. And so many of these packages actually fail those tests. And so what they do is they refuse to, the developers of R, they refuse to allow you to put up your package on the CRAN archive. And instead, they will put your package on an archive here, which you will see here. So now what you should do is click on the archive and look at the most recent version of the bivariate package. That's this one here, okay? So here's my bivariate package. So as you can see that I already downloaded it earlier. And so that's why I've got these brackets too here, because this is my third version of the bivariate package that I just downloaded, right? So you download the latest version of the bivariate package, and then you can, I think it's possible to install this package. Um, might be possible to install this package from the downloaded version, right? So install from repository. Yeah, here, see that? It says instead of installing the package from the repository, install it from the package archive file, which will be a tar gz file. Okay, so let's do that. So I go to my downloads folder, and here is my package which I just downloaded. So if I were to now click open, it'll probably try to install this package for me. So I'm not going to do that because I already have it installed. So when you do this, what might happen to you, or what will probably happen to you, is that it will install this, try to install the package, and then it will ask for other packages that need to be installed also. So just keep doing this process until you've got everything installed. And those other packages might also be on the archive because they may not be allowed to be on the CRAN archive. So you would have to, it's pretty tedious, I admit, but you would have to download each of those packages. So there's three of them, okay, that you will need to download if you want to be able to plot this figure, okay? So if you're really interested in being able to reproduce this figure, you'll have to figure out how to download those packages. But I showed you how to do that now, okay? So you just manually install the package from the tar gz archive, okay? So that's how this will work. If you run into trouble with not being able to install those packages, right, then either talk to Johan or come to me after class and I will show you how to do that, okay? I can demonstrate that to you on your machine, okay? So that's a pretty straightforward thing, but it's not a big deal to install these archive packages from the internet. Okay? All you have to do is download the actual package and then do a manual install the way I just showed you. So that's basically it. And of course, I should mention that you don't actually have to install the bivariate distribution package to plot this figure. You don't necessarily have to reproduce every single figure in my slides. What is really important for you to be able to do is to actually work with a joint probability mass function, compute the marginals, compute the conditional distribution. All that is paper pencil work. You don't actually need to install all these packages for that. If you want to do it, of course, for fun, to be able to visualize your own bivariate data, then of course it's useful to install these packages. Or if you just want to reproduce my figures, you should certainly install the packages, but you don't have to do that. Okay, so that's it. That's all I wanted to talk about. And um, in the next class, I will build on these materials and introduce some more ideas about maximum likelihood estimation in the class. We'll do some exercises and I will talk about bivariate and multivariate distributions and give you some practice in generating some simulated data in the class itself.